Moving on from kinetics, we're going to now study chemical equilibrium. Well, we'll start off with a brief introduction to what equilibrium means. We'll take a look at something called the equilibrium constant and how we can apply the equilibrium constant, and then we'll look at several other applications of equilibrium as we move through this chapter. To start with, the concept of equilibrium basically just means that we have, most of the time we think of reactions happening in one direction. Well, the reality is that most reactions can happen in both directions. So in the pictures that we have here, we have an equilibrium that's established between the N2O4 producing NO2 and the NO2 reacting backward to produce N2O4. So notice the way that we draw the arrows for this, each one is a half arrow pointing in the opposite direction. So this represents an equilibrium where it can go back and forth from reactants to products, products to reactants. And in the pictures here we have, you can, hopefully you can tell that what they've done, what they've changed here is that the beaker container on the left is much colder. And so what's showing you is that the amount of product or reactant depends on several factors, one of which is the temperature. So in this case, in a colder environment, you're going to favor the formation of the N2O4 and have less of the NO2. At a warmer temperature, a higher temperature, it would favor more of the NO2, and so you'd have the equilibrium shift over to that part there. So we'll kind of get to that concept or that part of equilibrium toward the end of the chapter. If we were to graph the rate of these reactions, we would see that the rate in the forward direction, which would be the formation of the reaction of the N2O4, which is the blue line in the picture here, would slowly decrease. The rate of formation of the product would slowly increase. When the rates in the forward direction and the rates in the reverse direction became equal, that's where we would have that state of equilibrium is achieved. So again, we had the rate forward equal to the rate reverse. So we would then have a state of equilibrium or balance that would occur. Now notice that this does not mean that we would necessarily have the same amounts of each of the reactants as we have the products. It just means that the rate at which the reactants are forming products and the rate at which the products are forming reactants is the same. If we look at the concentration versus time, you can see this, where the concentration of the product, the NO, the red line here, increases over time, and the concentration of the N2O4 decreases over time. At equilibrium, the concentration of both of these will remain constant, but again, notice that they do not necessarily have to be, the concentrations don't have to be the same. If we look at this quantitatively, with the rate forward equal to the rate reverse, and from our study of equilibrium, we know that rate forward, or the rate reverse, would be equal to a constant times the concentration of the NO2 squared. The rate forward would equal to a constant times the concentration of the N2O4. Since these two rates are equal, we can equate the two of them, and we get the expression here. If we rearrange this, then we get this expression, where we can have a constant then is equal to the concentration of the NO2 squared divided by the concentration of N2O4. Now, we did make an assumption here. We assumed that the rate in the forward direction and the rate in the reverse direction were equivalent to elementary reactions. In other words, we could take the stoichiometry or the coefficients in the equation and use those as the order for each reactant. In this case, it's going to work out that that's possible. And we'll see the kind of generalization of this idea in just a moment. When we take those two constants and we put them together, basically what we're creating is what's called the equilibrium constant. Okay? So that's the KEQ. So our general statement for this is related in something called the law of mass action. So you can see here, if we take a general equation, general equilibrium equation, AA plus BB going to CC plus CD, or DD, as an equilibrium, we can say that the equilibrium constant, the Kc in terms of concentration, is equal to the concentration of each product raised to the power of their coefficient divided by the concentration of each reactant raised to the power of their coefficient. Looking at some different equilibrium expressions then, we can write down the equilibrium constant expressions for these. So if I take the first expression, I would say Kc would be equal to the concentration of the tin times the concentration of the carbon dioxide squared divided by the concentration of the tin 4 oxide times concentration of the carbon monoxide squared. Likewise, I could do the same thing for the second one. Kc equals the concentration of the calcium oxide times the concentration of the carbon dioxide divided by the concentration of the calcium carbonate. Now, we're going to find out that in our next segment that we're not going to end up including solids and liquids in this. One of the things about solids and liquids is that their concentration is not going to change. So they would end up getting left out of this expression, but we'll cover that when we talk about heterogeneous equilibria. And obviously you can take a look at the last one then, but we'll come back to these again when we talk about heterogeneous equilibria. One of the things that's worth pointing out is that equilibrium is non-directional. So if you take a look at the last two experiments in this study, in experiment 3, you're starting out with none of the nitrogen dioxide. You're starting off with all nitrogen dioxide. And you can see by the red line that that concentration is going to decrease until equilibrium is established, and then it will plateau. In experiment 4, you're starting with none of the nitrogen dioxide, so you have only the N2O4. And in this case, this is a blue line, that concentration goes up, and you can see that it's going to continue going up until it gets that same concentration that we had in the other one where you started with purely just the NO2. So equilibrium is non-directional. You can reach equilibrium from either starting with all products, all reactants, and a slightly more complicated case, but one we're going to learn to deal with, a combination of both products and reactants. Here's another example from the Born-Haber cycle, so the formation of ammonia. You can see that whether you start with the hydrogen and nitrogen as we do on the left, so the hydrogen and nitrogen are going to decrease. Those are the green and blue lines on the left. And the amount of ammonia, the concentration of ammonia, will increase as time goes on. They're going to reach those same equilibrium concentrations over time, whether you started with the reactants or with the products. Looking at the equilibrium constant, one of the things we're going to want to do is examine not just the equilibrium constant in terms of concentration, but particularly if we're dealing with gases, we might want to work with pressure. So up here we put down the combined gas law, or the universal gas law, PV equals nRT. We've rearranged it slightly so that we put the N over V, which is concentration or molarity. So what this is showing is that pressure of say substance A, is equal to the molarity of A times a constant, or in other words, the pressure of A is proportional to the concentration of A. From that, we can deduce then that the equilibrium expression we use for concentration can be used to apply to gases and pressure. So the Kp, so the equilibrium constant in terms of pressure, would be the partial pressure of each product gas raised to the power of their coefficients divided by the partial pressure of each reactant raised to the power of their coefficients. Relating Kc and Kp together isn't horribly challenging. If we take that same expression and take a look at it, if we rearrange the variables here, we end up with this expression here relating the Kp to the Kc. Now, this is going to be useful for us if we are able to measure the equilibrium constant in terms of pressure or in terms of concentration, but want to solve for the other one. It's important to realize that the delta n, all right, that's used as the exponent for RT, and T obviously has to be in Kelvin, that delta n is equal to the number of moles of gaseous product minus the number of moles of gaseous reactant. So keep that in mind as you do practice problems with these. So we have a couple of final points. The first one is that the magnitude of the equilibrium constant can tell us a great deal about the reaction. So for instance, in the top example here, an equilibrium where most of the matter is going to lie on the product side would give us an equilibrium constant, a K value that's much greater than 1. Obviously, it's products divided by reactants. And an equilibrium value that was very small, as the one on the bottom, would indicate that there was a relatively large amount of reactants compared to the amount of products. So when you look at the magnitude of the equilibrium constant, it can tell you about those two things. Obviously, an equilibrium constant around 1 would tell you that there's relatively the same amount of reactants and products. If we reverse a reaction, so if we take an equation and we flip it over, the equilibrium constant, if you notice, flips over also. So in the top one, you've got the equilibrium constant for the reaction of the N2O4 forming NO2, which would be 0.212 at 100 degrees Celsius. And in the second equation, you flip that over, and so we have the concentration of the N2O4 divided by the NO2 squared, and so we would just take the inverse of that value. So you can see those given to you here. So they're just inverses of each other. The other thing that we want to be kind of prepared for is what happens if we do multiples of the equilibrium expression. So the first one, again, is the N2O4 going to 2NO2. In the second one, we are doubling the amount of reactants and doubling the amount of products. And so now, it's a little bit different, a little bit surprising here, is that if we look at the equilibrium expression, we end up squaring the value for the equilibrium constant. Right, so if we double the equation, which we could do in terms of if we kind of applied Hess's law or something like that, if we doubled the coefficients in the equation, we actually square the value for the equilibrium constant. So this is where we'll leave off for right now, and we'll pick up, as I mentioned a little bit earlier, the heterogeneous equilibrium when we come back.